let us come back and finish off the last chapter of your grade 12 syllabus, that is polymers. The easiest chapter, I should say. Even if you're not like last for 1 week also, you can finish off this chapter. So this is part of your part 2 book, unit 15. Let's see the index, what we are going to learn. So basically from this chapter you'll be getting two types of questions. What are they? They will give you the polymer. You need to write the monomeric units, right? They will give you the whole compound. Polymer, you need to write both the monomers, two different units. That is one type. Or they may ask you what are biodegradable polymers, in that way. Or they may ask you uses. What are the uses of any of these compounds? Let's see the index. So in polymers, we'll be studying the classification of polymers, which is based on the source. Again, you have types in that. Classification based on structure. Again, you have types. Based on mode of polymerization. Again, you have types. Addition and condensation polymerization, like that. Okay, we will do that mode. In what way is it linking? Next would be the molecular forces, based on the classification based on molecular forces. Next would be growth polymerization. After classification, I'll be going into the types of polymerization reaction, that is addition polymerization. Under that, I'll be teaching you about free radical polymerization. I'll be showing you the chain initiation step, termination step, initiation step, propagating step as well as terminating step. Then after that we are going to learn about condensation polymerization. Then I'll also be teaching, after addition, condensation, I'll be teaching you what are copolymers, right? One question was asked once. Copolymers, it may be like two different monomers combined together. Next I'll be finishing off the chapter with biodegradable polymers. Done. Then there's a small topic which will teach you how to calculate molecular weight of polymers. So once we are done with the index, let us start doing. What I'll do is I'll try to teach you in a different way how to remember this particular polymer chapter. Let's come back and start with your polymers chapter. Basically, your whole polymer chapter, the question which is asked is, in the complete chapter, they will ask you, now they will give you a polymer. Done? They'll give you an example and they will ask you, write the monomers of them. That is one way. Or they may give you the monomer and they ask you to write the polymer of that. Or they may give you the polymer and ask you to write the uses. So everything I tabulated in one column. All the examples of the chapter will come under this. Basically, when I taught you the index, I told you polymerization is studied in addition polymerization, condensation polymerization, copolymerization, homopolymerization, biodegradable polymerization. This was the index which I discussed. So what did I do? First, I picked up the set for addition polymerizations. So all these are addition polymers. 1, 2, 3, 4, 5. 5 are addition polymers. Then I'll be gradually going into condensation polymers. Then after that I'll go to types of rubbers. Then I'll gradually go to copolymers. Then homopolymers. Okay, let us not get confused. Let's start with the first topic of your polymer chapter, that is which comes in the category addition polymerization, and the compounds or the examples are polythene, polystyrene, polyvinyl chloride, that is PVC. Next, Teflon, that is polytetrafluoroethylene. Next, PAN, right? That is called polyacrylonitrile. Okay. So basically in the exam they will give you this. You need to write this part and this part. Let's start. So I've already written the uses here. Uses, you need to remember all the uses because they may ask you for 2 marks. Applications of uses. When I speak about polyethylene, as the name suggests, see here, ethene means 2 carbon compound. So when I have to write the monomer of that, C double bond C is ethene. Now fill the hydrogens, H2, H2. This is the monomer of polyethylene, single unit. There's nothing else. Now when I have to write the polymer of this, the bond here breaks up and what does it form? You're going to write a square bracket. 2 carbons are there, 2 carbons linked with a single bond hydrogen because this has already broken. Done. So CH2, now CH2. Now ma'am, this is 2 plus 1, 3 and the 4th one is here. On the other side also the 4th one is here and you will write a small n. That means the chain continues in that way. So this is called polyethylene. So polyethylene. So polythene is this. This is ethene. Monomer is ethene. Let's come back and write polystyrene. Nothing. Styrene, whenever you see styrene, that means there is a benzene ring along with this. That's why I've written in a sequence. This is your double bond, isn't it? Now see, write the same, CH2. So here CH2, I'm copying the same ethene here. Done. Now you're going to fix a benzene ring to this. Now count the number of hydrogens. 1, 2, 3, 4. This is styrene. So simple, styrene is a monomer. Now when I have to write the polymer of this, what will happen? The bond here is going to break and this opens up. How does it look now? C, single bond C, H2 long, because this bond has broken up and the bond continues. This N is already there, it means it is a polymer of that, and your benzene ring is present below. Link it. Now what happens? 1, 2, isn't it? Yeah, 3 hydrogen and the fourth one. 1, 2, 3, 4 and N. This is polystyrene, the polymer of that. This is styrene. The polystyrene means number of chains increase. Polymer means many units. Now when I have to write PVC structure, now see, PVC and PAN. PVC and PAN both are almost similar, but only thing here you have chloride, here cyano. So remember, PVC structure and PAN structure are same, both are similar. PAN means polyacrylonitrile. Applications are also given which are used for making synthetic fibers. Let us write. So vinyl chloride. Okay, let us forget about this. Vinyl chloride we've already learned. What is vinyl group? We have studied two groups, allylic group and vinylic group. So vinylic group is something where you have double bond this one to adjacent carbons and you have a chloride attached immediately. So fill in carbons. Now this is CH2. Now 1, 2, right? This is 1, 2, 3 and you have your hydrogen. Done. Let me see whether I've written correctly or not. Now to this carbon 2 hydrogens, to this hydrogen 1, 2, 3, 4 and chlorine. Now this is called vinyl chloride. Vinyl chloride. Now let us write the same for PAN also. I said both are same almost. Now same C double bond C. Now in this case, instead of Cl, as the name suggests, acrylonitrile. Nitrile means CN group. Fill CN here. Now same CH2 and CH. Done. This is called acrylonitrile. Acrylonitrile. Now write the polymer structure of that. This is going to break. See that always you're linking or continuing the change from hydrogen. Drop this on. Put a square bracket in this way. Now CH2, right? Done. The chain is continuing. There is single bond and your CH is here and drop the Cl down. And this chain continues here. Now see, for this hydrocarbon 1, 2, 3, 4. For this hydrocarbon 2, 3, 4. All are balanced. So this is called PVC, polyvinyl chloride, which is used for making raincoats, vinyl flooring, leather clothes and all those. So let us come back and write for this. What should you do? You have to break a bond here and try to show the continuation of the chain. So write exactly same. C single bond C. Drop the Cn down. Cn. And fill both the cell on either side. Now hydrogen is still existing here. CH2. Here hydrogen is still existing H and N. Every time you need to represent that N. To this hydrogen 3, 2, 3, 4. This hydrogen 1, 2, 3, 4. This is called PAN, polyacrylonitrile. This is polyvinyl chloride, polyacrylonitrile. Let's come back and write Teflon. Teflon full form is poly tetrafluoroethylene. So ethene, whatever it is. Now here ethene I said, isn't it? Ethene means 2 C double bond C. Now basically ethene is CH2. Now what is going to happen? Tetrafluoro. That means instead of hydrogen there are 4 fluorines. How? Hydrogen you are replacing with CF2 double bond CF2. This is Teflon, or this is called PTA. This is TFE. This is Teflon. Now how should I write the polymer of this? You're going to break this bond, make 2 square brackets, C single bond C, because the bond is already broken, becomes single bond. Never in polymer you have double bonds. Now C F2 continuation CF2 continuation polymer. That's it. So these are your addition polymers. Simple thing. See the name, write the monomer, break this bond, finally write the polymer and write N. Everywhere you need to name the compound. So what is this called? This is called Teflon, tetrafluoroethene. So what should I call this? Right? This is only like this is also Teflon, this also, but here it is PTFE, polytetrafluoroethene. So can I write this as PTFE? Yes. Here I should not write PTFE because this is not polymer. This is only Teflon, tetrafluoroethene. Let's come back and start with the next type of polymers, that is condensation polymers. So we have listed out 1, 2, 3. We still have 2 more to learn. So in the exam, they may ask you either the uses, as I said earlier. They'll give you this compound and ask you to write the names of the monomers, only names. Lucky enough if you get that. Or they may ask you to write the structures of monomers, or they may ask you to write the polymer of that after condensing. So basically, whenever I speak about condensation polymerization, you have to remember that 2 different molecules are going to combine to form one molecule that will continue, that forms a polymer, repeating units. During this process, it's going to lose water molecule, that is dehydration is going to happen. Done. When I have to speak about dacron or terlin, whose uses are already given, as the name suggests here, ter means terephthalic acid. Ene means ethylene glycol. Okay, I'm writing both the structures. See how are we going to condense. So I'm going to start with ethylene glycol, OH, CH2, CH2, OH. This is ethylene glycol. Okay, I'll take out this hyphen here, and N moles. I'm going to condense this with terephthalic acid. You have a benzene ring in the center for terephthalic acid. You have carboxylic groups on both the sides. This is also N moles. Now, during condensing, look here, this H and this OH condenses. It's lost. Second, because you have lost one H from here, try to take out OH from here and H from here. That means 2 water molecules have lost. Now combine together to form a polymer. Try to put square brackets in this way. Continue the chain and write N. Now start from here. Already H is lost here in form of water. You have O, CH2, then CH2. These 2 condense together. You have CO. Careful now. O and C double bond O, benzene ring. And it's linking with O, and this is continuing. This compound is called terlin or dacron. Done. Next, let's come back and do nylon 6,6. So nylon 6,6 basically is made up of 2 monomeric units. Remember that. I'll show you why we have got written this 6,6 also. First, the first monomer of nylon 6,6 is, look here, how am I writing? Hexamethylene diamine and adipic acid. Here it is terephthalic acid, here it is adipic acid. So hexamethylene diamine, that means there are 6 methylene groups. What is methylene group? CH2 taken 6 times. Hexamethylene is over. Diamine means on both the sides you have NH2, here also NH2. You're going to add with adipic acid. Adipic acid is nothing simple. Just like your terephthalic acid, you have COOH groups on both the sides. But in the center, you have 4. How? Just see. 6,6 I said, nylon 6,6. Here there are 6 carbon atoms, methylene groups. Here also there are 6. How? 4, 5 and 6. Total 6 and 6 joined together to form nylon 6,6 polymer. So how should you remove? This is under 553 Kelvin, high pressure if it is condensed. How is the water molecule lost? sorry, 2 water molecules are lost. From where are they lost? H from here. Observe carefully. 1 H I am taking out from here. When you're taking 1 H from here, immediately take out 1 more OH from here. Done. Now come back to this, because from here and here condensed. I need to condense these two. Observe carefully. 1 H from here. Done. Now let us write COOH in this way. Easy, isn't it? COOH. I've taken H from here, so I have to take out OH from here. Now join. Make a square bracket in this way. N. Done. This is also N moles. This is also N moles. When they combine, you write it in this way, which represents the polymer form. Now first what happened? NH. Okay. You can write H also like this. NH. Yes. Then how many are there? CH2 taken 6 times. Now this N has become NH. Next, this all water is OH is lost. You're left with C double bond O. Then CH2 taken 4 times. Now C O. Now observe carefully. There is a formation of amide group in between. Look here. NHCO is an amide group. That's why nylon 6,6 comes under the category of polyamides. They'll ask you, write an example of polyamides, then you'll write this example. So this is nylon 6,6 because 6 and 4, 5, 6. So see here, there are 6 carbon atoms here, 6 carbon atoms. So this is nylon 6,6. Done. Let's come back and write for nylon 6 now. So nylon 6, the monomeric unit is caprolactam. Caprolactam, nothing simple. It is a cyclic chain. How should you write? Try to first write NH on one end. Then join this with C double bond O. Now from here you have to remember there are 5 carbon atoms. Okay, now this don't start from here. Okay, this is already over. 1, 2, 3, 4. Now count 1, 2, 3, 4. And the fifth one. Let's count again. 1, 2, 3, 4. Right? 4 and 5. Fifth one is this. Done. When I'm supplying almost 543 to 553 Kelvin temperature, right, when it is heated, this chain opens up. When this chain opens up, it becomes a straight chain. How many? CH2 taken 5 times. Okay, if I have written wrong, let us see. Count 1, 2, 3, 4, 5. Done. So CH2 taken 5 times. Now what do you have? You have NH on one side and you have C double bond O on one side. Done. So this extends, this also extends. You can write like this, C double bond O, this becomes. So this is your nylon 6 because 5 plus 1, 6. Nylon 6. That's it. Right, after addition and condensation polymer examples, let us come back and do a third category of example, that is bakelites. Okay, bakelite, we will also study one more type, that is melamine formaldehyde. Basically, when I speak about, these are also a class of polymers, but here what are we going to do? We are trying to combine or form, right, a compound called bakelite, right, which is used in making combs, handles and electric switches and all these. How are we going to do? We are going to first pick up formaldehyde and we are going to combine with phenol. I'm going to take phenol, and then combine with formaldehyde in the presence of acid and a base catalyst. Okay, then let us see how is this basically made. Now, first important thing, try to pick up phenol. Done. Easy. After writing phenol formula, you are going to write formaldehyde. So what is phenol formaldehyde formula? Formaldehyde is HCHO. I can write HCHO as, see here, CH2O. Correct. So I'm going to write CH2O. This whole thing, this condensation occurs in the presence of an acid or a base catalyst. These are catalysts, acid catalyst or base catalyst. Now in initial step 1, just observe carefully, this H plus is picked up by this, means that in the presence of that catalyst. So what product do I get? I am going to get 3 different compounds. First OH is there. I am going to get ortho compound, orthohydroxy or orthomethyl hydroxy compound or hydroxyphenol. Then I am going to get one more compound where here I've got ortho product. Now I'll be getting para product also. I'll also be getting one more product, that is ortho, para, again ortho. 3 products together. 3 products together, OH, CH2OH, CH2OH and CH2OH. Done. Now what's going to happen? All the 3, please don't get confused, all the 3 ortho, para and para compounds. Now what happens further? These compounds are going to, like if I pick up one, let me take out this. Further, when it is treated with your this in the acid or the base catalyst, what's going to happen? Just see here, I'm taking the same compound. Okay, let me write that here again. I'm taking the ortho compound CH2OH. Now this further, if it is treated in the presence of an acid catalyst, now observe carefully. This whole compound, it's going to start linking one after the other in a linear way. How does it link? There is condensation of water. Observe. So one OH from here. Now observe carefully. This is one OH. This is going to link with one more CH2. Again you have one more CH2 in this direction. Means they are linking. This links. Now this CH2 links one more ring in OH. Then again this CH2. So in this way the chain continues. This goes on. This linear condensation of polymer, linear formation of polymer, if it linearly forms like this, then I call it as Novoloc, linear polymer. This Novoloc is used in paints. Yes, so this linear condensation, what did I do? I've taken it again in the presence of H plus and removed it. Done. Suppose if I have to make, now this is Novoloc. From the Novoloc, we are going to prepare bakelite. How are we going to do? The same thing. If it again cross links. What does this happen further when it condenses? What are you going to do? You are writing one layer here. Just observe. One ring OH, one CH2 here. Okay, then this is again CH2 linked with one more ring. I am not drawing many. I am just drawing 2. Done. Now again one more layer. You also have one more layer down. This is OH. Now this will be OH down. Right. These two are linked by CH2. Cross links. Now again this is CH2. This is again CH2 on this side. This is CH2. One more ring. Cross linked. OH below. This is CH2. And this is also linked with CH2. Done. So now what's happening? They are cross linked. This cross-linked polymer is called bakelite, which is used in electrical switches. All these I've written already, handles and everything. Novoloc is a linear polymer. Bakelite is a cross-linked polymer. The strength of this is more than that. Right, now let's come back and learn the next type of resin, that is melamine formaldehyde resin. Basically, whenever we see melamine, we very well know it is used in crockery items. Okay, simple. Now earlier what did we learn? We have prepared a linear polymer, that is Novoloc, cross-linked polymer, that is bakelite. Now here in melamine formaldehyde resin, basically it's very simple. Let us first write the formula for melamine. For melamine formula, you have 3 nitrogens first. Join them 1, 2, 3, 4, 5, 6. Now, you have on the corners NH2, and you have double bond here, double bond here, double bond here. Now I'm going to combine with formaldehyde HCHO, which I can write it as CH2O. When these two together combine, see here, one H from here, so this, what do I get then? I'm going to get N, benzene ring type like this one, with NH2, 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 N, N. But here H is already donated, means this is shared by CH2OH. This becomes NHCH2OH. Now draw the double bonds. This is called resin intermediate. Resin intermediate. Resin intermediate. Now this on further polymerization, when further polymerizes, here one H from here and one OH from here is lost. Now how does this look? This becomes nitrogen, N, N. This is NH2 in this way. Okay, now one is lost, isn't it? So this ends up the chain, this terminates the chain, NH. Now you have NH2 here. Now careful. Here I said NHCH2. Done. This also terminates. Now draw the double bonds. Yes. This is called, what is this called? This is called melamine formaldehyde resin, which is used in crockery. Welcome back, students, to one more session of your polymer chapter. So in polymer chapter we have studied addition polymers, we have studied about condensation polymer examples. Then I taught you about two types of resins. One was bakelite formaldehyde resin, that is which forms a straight chain. Then straight chain polymer, then we call it as novella. If it is a cross-linked polymer, then we call it as bakelite. Then we have also learned about phenol formaldehyde resin. So let's come back and start with a fresh topic, that is rubber. So for your grade 12th, you are going to learn about two types of rubbers. One would be natural rubber as well as synthetic rubbers. So you have the structures of natural rubbers to be learned and synthetic rubbers also to be learned, right? Like neoprene, we'll be doing all those. So basically whenever rubber concept is given to you, try to start your answer. If they ask you what is natural rubber, right? First try to write your answer starting with the nature of its rubber. What is actually a rubber? When you try to stretch it, it stretches, isn't it? That is why we call rubbers as they come under a category called elastomers, where you can stretch them. When you stretch and release, they retain the original structure. So what are rubbers? Rubbers are elastomers, right? As I said, it can be stretched and are held by weak intermolecular forces, or if I have to say, van der Waals force of attraction. Van der Waals forces of attraction. Right. Now, so because of this, they retain back their structure. Done. Now, what is the source of, where do we get this natural rubber? So, I'm speaking basically about rubber. In that, I'm talking about natural rubber. So, later I'll be doing synthetic rubber. So, in this natural rubber, we very well know we obtain it from the latex of the rubber tree. So, let us write the source. This would be the definition. Then, when I have to write the source, done. It is from latex of rubber tree. This is also fine, but basically this is next. The structure is important for us. So when I have to write the structure, or if they ask me what is the formula for rubber, natural rubber, important, you have to write. It is basically or we write it as 2-methyl-1,3-butadiene. Okay, let us write the formula first. Formula is 2-1,3-butadiene. So the many elements here, let us write. So first of all, what is the parent atom? Parent atom is but. So let us write but. 1, 2, 3, 4. But. So in first position and third position, they are dienes. Means there are di means 2, E means double bond. So if I start numbering 1, 2, 3, 4. So first position and third. So 1 and 3. Butadiene. So they said 2-methyl. So in the second carbon, there is a methyl group. This is your methyl group. Now fill in all the hydrogens. So CH2, this there is no hydrogen because already 4 valencies are satisfied. 1, 2, 3. Here there is 1 hydrogen, here 2 hydrogens. This is called your natural rubber. So basically when I have to speak about natural rubber, when I go into the structure, we call them, other than 2-methyl-1,3-butadiene, we also call the structure as cis polyisoprene units. Okay, polyisoprene units. What is this basically? When I say cis means on the same side. Poly means many. Isoprene units means if they have 5 carbon atoms linked, then it is called isoprene. Once again, cis on the same side. Poly means many, isoprene means 5 carbon chains. See, I am writing the same structure in this way, where you are going to form the polymer. Just observe carefully. You have the CH2, isn't it? CH2 double bond. Look here. Now CH2, now C single bond, C double bond C. Now you have one CH2 here, one more CH2 here. Okay. Yeah, and one side there is one hydrogen here, done. There is one CH2. Now see here, 1, 2, 3, 4, 5. If there is a 5 carbon chain like this, we call isoprene unit. So what happens? One isoprene unit links with the other isoprene units from CH2 bond, not the H1, from CH2. So this is going to link with one more CH2. Now this is again joined with C double bond C. Now CH2. Now H and okay, we will write like this also, not a problem. Yes. Now you have to be careful. What did I say? Cis isomer. Now cis, see here, same side. So here also, if I have to say speak, this is also same side. Now what happens? Cis polyisoprene. Now if I have to link here, now observe from CH2, again it's going to link with one more CH2, this again from C double bond C, H, CH2 and CH2. So in this way, this is going to form an isoprene unit, polyisoprene unit with all the cis bonds, cis here, cis here, cis here. So this is also called as cis polyisoprene. These two are the names. You can just put it in box for rubber, natural rubber. This is the structural representation. Now when I have to see the structure of natural rubber, what are you finding? Basically it is spirally coiled. Right, it's spirally coiled. So I can, that is why I when I apply certain force, elastic force, it will stretch, and when I release, it will again go back. So spirally coiled, and it acts as, and same thing I'm writing here, elastomer. Yes, done. So I already wrote what are the weak forces of attraction, that is van der Waals forces of attraction are existing in them. Done. So that because of this spirally coiled and this one, I can say this particular thing. It will, when I apply certain amount of temperature on this, it's either going to become soft or it's going to become brittle, right? So this nature is affected by temperature. We will see what is the temperature. So now because of this particular concept, we are going to learn one more in extension concept called vulcanization of rubber. So let's come back and read or learn what is the process of vulcanization. Right, let's come back and learn the concept of vulcanization of rubber. So basically, when I speak about rubber, I already learned the structure, that is, it is also called as cis polyisoprene unit, having 5 carbon atoms. Now, when I have to speak about vulcanization of rubber, why should I do vulcanization? What actually is this? Let's see. So when I said rubber is an elastomer, done. So when I apply a temperature, I also said one more point, whenever temperature is applied, its structure is affected. How is that? This rubber basically is going to become soft when the temperatures are raised. When the temperatures are greater than 335 Kelvin. When you raise the temperature to 335 Kelvin, it will become soft. And it is going to turn brittle when the temperatures are less than 283 Kelvin. Both the conditions, both the ranges. So now what to do? What actually is this? We can't, like, we need to maintain the temperature and maintain that stiffness in rubber. So when they have observed the properties of rubber, first important thing is it has high water absorbing capacity. Rubber, when I see, it will absorb, because when it is soft in nature, it's going to have high water absorbing capacity. Okay. Now, second, when I take this rubber, instead of its durability, when I try to dissolve it in non-polar solvents, like benzene, alcohol, or this, it's going to dissolve in them. So, next important point you have to write is soluble in, because if there is non-polar solvents, right, this also is a problem. If it's soluble, non-polar solvents, it should not be soluble, isn't it? It should be stiff and durable enough to use for many years. It's important, they are non-resistant to oxidizing agents. Okay, because of these properties, what do? They are going to improve all these properties. They are going to vulcanize rubber. Basically, you are going to add sulfur bridges into this rubber. So to overcome all these, okay, so we are going to do what process? Vulcanization. So let us write the definition. Basically, right, so what is the vulcanization process? It is a process of increasing the strength of rubber, right? What are we doing? We are trying to modify the rubber structure by adding certain additives. We will add certain accelerators. I'll show you that also. So what we do, we try to add sulfur. So 4% sulfur is a standard thing which we use it for tires for its durability. Like that, I keep adding sulfur bridges wherever you have double bonds. So vulcanization is a process of modifying rubber. Let's write that. It is a process of modifying rubber, right? I have to improve all these qualities, isn't it? Rubber by adding sulfur bridges. Now along with that, I'm also going to add certain additives or accelerators. Sulfur bridges, where are you adding sulfur bridges? Around double bond to increase. Why are we adding this? To increase its strength. I want that stiffness in that rubber, not too strong enough, not too soft enough. I want that flexibility of rubber. So sulfur bridges around double bond to increase the strength of rubber along with accelerators. Okay, I'll give you certain examples. Accelerators. Okay, accelerators like, okay, I'll give you one example, you can remember that. The accelerators are called, or one example is sulfinamides. Sulfinamide is an accelerator which will increase the strength also. The formula for this is, you have sulfur, you have N, you have alkyl group here. When you have alkyl group, one more alkyl group. This is called sulfinamide. So this is the definition. Once again, it is a process of modifying rubber by adding sulfur bridges where around the double bond. Why? To increase the strength of rubber along with certain accelerators like sulfinamide is called vulcanization of rubber. Done. So let us come back and see where are we at bridges, isn't it? So because of this, the stiffness or the strength of the rubber increases. So let us write, because of vulcanization, the stiffness, or if I have to say stiffness, I should not say but clearly stiffness, I could say increases the strength of rubber. Okay, the durability of rubber, or increases durability or the strength of rubber. Okay, done. So how are we going to add? Now basically you can draw the structure. Now what do we have? It is 2-methyl 1,3-butadiene is your rubber. Done. So how should I write this? 1, 2, 3, 4. This is the second carbon, methyl. First position, third is double bonds. Now you're going to add sulfur bridges wherever there are double bonds. Now break this bond, add one sulfur bridge. Break this bond, add one sulfur bridge here. So how are you adding? Now you are going to break this bond. You're also going to break this bond, add one sulfur bridge to this. Add one sulfur bridge again to this. You have, now see here, one more CH3 on this side, C on this side, now C on this side. This is linking. Done. Now this carbon is like this, isn't it? C. I'm talking about this. Okay, double bond, done. So like that, if I have to draw the structure, it's basically, this is one carbon chain, this is one more carbon chain, you're linking everywhere with sulfur bridges. So the sulfur bridges will increase the strength of your rubber. Now what percentage? If I have to speak, it is most 5%, 4 to 5% is a 5% sulfur. If I have to say 5% sulfur is used as a cross-linking agent. Okay, 5, let us write that. 5% sulfur acts as cross-linking agent along with accelerators, accelerators. So this is the thing. So this is how you're going to write your vulcanization of rubber. Start with the properties, then come back to definition, then come back to the outcome, then draw the structures and what is the how much percentage is used. Back and learn about synthetic rubber. We have already learned about natural rubber. We've learned the structure and also studied about vulcanization of rubber. So whenever I have to speak about synthetic rubber, basically if I have to define synthetic rubber, it is same like rubber only. It is also called as vulcanizable rubber, which I can stretch, means I can add sulfur bridges and stretch. So first synthetic rubbers are also called as vulcanizable rubbers, which can stretch. Done. So basically when I have to speak about synthetic rubber, you can stretch almost, you know how much, like twice the length of its, you can stretch 2 times more than its length. Again, when you release it, they revert back to its original position. So because that is why we call it as elastomers, isn't it? Done. So let's write that. They can be stretched to twice their length. Because I have added sulfur bridges, I can easily stretch them. Stretch to twice their length, yeah, and can revert back to the original position, and can revert back to their original position. Okay, done. So original position. So when you're going to learn about your synthetic rubbers, for your syllabus, you have 3 types to learn. What is neoprene or chloroprene? Let us write that. So types in that, you'll be learning about neoprene. It is also called as synthetic rubber. This is synthetic rubber, or chloroprene, where you have chloroprene unit. Done. We will see the structure also. We'll write the monomer and dimer, monomer and polymer. After that, you have buna N. You also have buna S. Butadiene, acrylonitrile, butadiene, styrene. So let's come back and learn the structures and uses also for all these. Back and start learning the examples of synthetic rubber. So synthetic rubber, I said, the first example which we are going to learn is called neoprene, okay, or it is also called as chloroprene. So simple. Basically, we have learnt 1,3-butadiene, isn't it? Then earlier, where in rubber we have learnt 2-methyl 1,3-butadiene. So this is simple. This is 2-chloro 1,3-butadiene. Nothing. Once again, natural rubber is 2-methyl 1,3 butadiene, that is natural rubber. Then this is what you have studied. Now synthetic rubber is 2-chloro 1,3-butadiene. That's a monomer. Let's write that. So 1,3-butadiene, write in 1, 2, 3, 4. In the first position and the third position you have dienes. So number this 1, 2, 3, 4. First position double bond, third position double bond. Again in the second position you have chloro. So this is neoprene. Let us fill hydrogens. 2 hydrogens here. For this, not required, all 4 are balanced. Here you have 1 hydrogen, here 2 hydrogens. This is your monomer of neoprene or synthetic rubber. Suppose if I have to write the polymer of this, see here. Now this bond, careful, is going to shift here. Observe carefully. From here the double bond is going to shift here. How does it look? 1, 2, 3, 4. This bond is going to shift here. I'm going to get a double bond here, and this will break up and open and form the polymer. So you're going to link it in this way, you're going to link it in this way and write N. So fill in the hydrogens. So 2 for this, 1 for this, 1, and for this 2. This is called the polymer of neoprene. This is the monomer of neoprene. This is the polymer of neoprene. Done. The next type is called Buna S. Okay, I have written the uses also here. You can check. So when I have to write Buna S, let us write first Buna N acrylonitrile. Then I'll teach you. So Buna means 1,3-butadiene. Look here. Buna means butadiene. N stands for acrylonitrile. Let us see the formula. In the monomers, write 1,3-butadiene 1, 2, 3, 4. 1, 2, 3, 4. In the first position and the third position, butadiene, fill in 2 hydrogens, 1 hydrogen here, 1 hydrogen, so 1, 2, 3, 4 and 2 hydrogens. This is 1,3-butadiene. I have to add to this acrylonitrile. What is acrylonitrile? Simple, isn't it? See here. Just write C double bond C. To one of the carbon add cyano group. Nitrile. Look here. Nitrile. This is cyano. So double bond exists here. So CH2, 1, 2, 3 H. This is acrylonitrile. Now you're going to add these two. This is the monomer. So you will write 1,3-butadiene is one monomer and acrylonitrile is one more monomer. They will ask you in Buna S or Buna N what is the monomer. So 1,3-butadiene, write the structure. Acrylonitrile is one more structure. So when these two club together, right, now remember, when I have to learn this tries to follow a mechanism like free radical halogenation we have studied, isn't it? Okay, I'll explain it later, you will understand better. Now as of now, remember this. So these two will add. How will they add? These two here. Now total how many other? 1, 2, 3, 4, 5, 6. Try to make 6 together. 1, 2, 3, 4, 5, 6. Then the 6th carbon you have cyano group. The 6th carbon you have cyano. This is going to end and it continues N. So I have to write N here. I have to write N here also. Here also I need to write N. Okay, done. Now observe carefully. Now here there's a double bond here. Careful. Earlier the double bond was here, isn't it? See here, 1 and third. Now the double bond is going to shift from this position to this position, second position, and this one it continues. Now fill in the hydrogens. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 2. 1, 2, 3, 4. This is called your Buna N. There's no place, so I have written here below. Don't write like that in the exam. These are the monomers. This is the polymer. Those are the uses. Right. I've done, I think there's a small mistake here. Please see here. I have not written chloro. Please be careful. So please correct this. This is chloro here. So there are no hydrogens here. Now, basically from conversion of 2-chloro-1,3-butadiene to your neoprene, the process or this is called polymerization. So this polymerization process, which mechanism does it undergo? This is going to undergo free radical polymerization. So let us write that. It undergoes free radical polymerization. This is the mechanism which you have learned in your grade 11. Free radical polymerization by forming one free radical, it keeps attacking again and again. Done. Here, from conversion of monomers to this, the process, this is because both are combining, isn't it? That's why this is called copolymerization. Copolymerization, it occurs in the presence of a peroxide catalyst. Peroxide catalyst. That's it. I'm sorry. Please correct this here. I've done. I forgot to write chlorine. Here you have chlorine. Yeah. Right. Now let's come back and learn the last type of synthetic rubber, that is BUNA-S. So when I have to speak about BUNA-S, BUNA stands for 1,3-butadiene and S stands for styrene. Okay, let us again write the same formula. Butadiene is 1, 2, 3, 4. So first and third you have double bond, diene. Right, that is what we have learned. So fill in hydrogen CH2. Here also CH2. For this only one hydrogen. For this also one hydrogen. Styrene formula is basically in styrene you have a benzene ring. To the benzene ring you have C double bond C attached. Earlier you had cyano group in acrylonitrile but not benzene ring, but here you have benzene ring to C double bond C and fill in hydrogens 2 and 4, and this is H. This is styrene. So the monomers of BUNA-S are 1,3-butadiene, I'm writing it again, and it is styrene. So these two undergo copolymerization, two different monomers, isn't it? So these two together undergo copolymerization process and they're going to form a compound. How does it look like? Now basically count 1, 2, 3, 4, 5 and 6. Let us write 1, 2, 3, 4, 5 and 6. Done. Now to this carbon, let me assume this is the last carbon. To this carbon you have your styrene ring. Done. Now I said from this the bond from here is going to shift here. From here it's going to shift to the second carbon. And this is going to continue the chain. This will also continue the polymeric chain. Let us fill the hydrogens. CH2, H, then H, CH2, 1, 2, 3, okay, H, and this is CH2. What is this called? This is called BUNA-S or BUNA, or we can write 1,3-butadiene hyphen styrene copolymer. You can write like that also because both have combined together. Done. So pick up 1,3-butadiene, BUNA and styrene. This is styrene. Write the formula from the first position. The double bond is going to shift to the second position and you're going to write 1,3-butadiene styrene copolymer. In earlier one, 1,3-butadiene acrylonitrile copolymer. So these are the properties and these are the uses. Let's come back and learn different class of polymers, that is biodegradable polymers. So very well know plastic has been the most these days which is causing cancer, right? So it has been usage of polythene or polyester, all these things. So it has been a challenge to the environment. So to prevent this, we are going to study about the preparation of biodegradable polymers. So whenever I speak about biodegradable polymers, the first important thing I have to write is it is a polyester compound. Done? Because you get an ester bond in between. So the biodegradable polymers are polyester compounds which are biodegradable and cause no pollution. So that's why we call it as biodegradable polymer. So when I have to take the example of this, right? Let us write how to name this compound. Basically, you start with writing poly. Okay? Yes. Then you can start writing beta hydroxy, right? Beta hydroxy butyrate, it's butanoic acid. The first is butyrate, co, that same thing again. Don't write poly. Poly already we've written. Again, right? Beta hydroxy. Here butyrate. Here it is valerate. So the full form is PHBB. This is biodegradable polyhydroxy butyrate and valerate. So if you have to write this, basically it is beta hydroxy butanoic acid plus beta hydroxy pentanoic acid. Done. Let us write the structures. So beta hydroxy butanoic. First write butanoic acid 1, 2, 3, 4. Name this 1, 2, 3, 4. So this is carboxylic acid. This is alpha carbon. This is beta carbon. To the beta carbon, you have hydroxyl group. Now fill in. Right, now let's come back and fill this. Now we said alpha and this is beta. Now let us fill the hydrogens. This is 3 here. For this carbon 1, 2, 3 and 4. For this carbon already 2 bonds are there in 2. So what is this called? This is called beta hydroxy butanoic acid. 4 carbons. Butanoic acid. Done. After that, we are going to add beta hydroxy pentanoic acid. Again, write 1, 2, 3, 4, 5. So pentanoic acid, 5 carbons. It's a COOH. The 1, 2, 3, 4, 5. So beta hydroxy. This is alpha carbon and this is beta carbon. So you're going to write OH. Okay, let me write on the top. So it's easy for me to take out OH. Done. Now fill in hydrogens. 3 here, 2 here, 1 here, 2 here. Done. So these together undergo, let us write the name also. This is beta hydroxy pentanoic acid. Pentanoic acid. Now there is a condensation polymerization occurring where there is a removal of water molecule. Then I'm going to remove 2 water molecules. Just observe, where am I removing? I'm going to remove 1 H from here. Observe carefully. 1 OH from here. 1. Done. So 1 H and 1 OH over. After that, I'm going to remove 1 H from here, 1 OH from here. How are they going to link? Now 2 water molecules are done. How are they going to do? Now start. Now here you are going to end your chain. First put a square bracket like this. Now your oxygen will end the chain in this way. Done. Then you have your CH. To that CH you have CH3 linked. Done. After that you have CH2. Then you have, observe carefully, C double bond OO, ester linkage, C double bond OO. That is, I said, polyester compound. So C double bond O is over. Now done. You have this carbon, isn't it, where your this one is, let link that. You take this as a side chain, this whole thing, drop it down as a side chain, CH2, CH3. Done. This part is here. This H is also there. Okay, let us write that H also. Done. 1, 2, 3, 4, and this whole chain is down. Let us make this further. Done. After this, we are coming back to the alpha carbon, CH2, and now CO, and end the chain like this. So observe carefully, H from here, OH from here. So you're ending with CO. hydrogen from here, OH from here, so you are ending with OH. So this is your ester linkage. This is called pH, this whole thing is called PHBV, polyhydroxy butyrate and valerate combination. You're getting this biodegradable polymer. Observe carefully, this carbon is here with hydrogen, that oxygen is taken as a terminal oxygen, the CH3 is down, the CH2, when I just come down, this is also there, the COO is forming an ester linkage, this CH where hydrogen is lost, OH is lost, you're getting the side chain down, CH2 and CO, this is called PHBB. Right. Now let's come back and start with the classification of your polymers. This is the first topic in your textbook, but I first felt to deal with the other topics which are very important, and let's start with this. Now in classification, basically we are going to classify polymers based on source, right? Then we are going to classify polymers based on structure. We are going to classify polymers based on the molecular forces which they have among them. So molecular forces, and we are also going to classify based on mode of polymerization, addition polymerization or condensation polymerization. So when I have to start this classification based on source, the first important thing, they are classified into natural with source. If it is natural polymer, semi-synthetic polymer, synthetic polymer. The first one, based on the source are natural polymers. Next would be semi-synthetic polymers. Next would be synthetic polymers. Done. So when I have to speak about natural polymers, nothing to define, which are obtained naturally from which are plant origin rather, right? Which are plant origin, right? Like naturally obtained. Okay, if I have to write proteins, polymers, cellulose is a polymer, resins are polymers, all these are naturally obtained, isn't it? Yeah, so you can pick up any number of examples. So when I have to speak about semi-synthetic, basically we speak about semi-synthetic polymers are those where you have acetate bonds, basically polyacetate or polyester bonds. So they are basically called polyacetates bonds, polyacetate bonds in them, right? So when I have to speak about synthetic polymers are man-made polymers. Like your rayon is man-made, polyester is man-made, yes, nylon man-made, all these are synthetic polymers, right? Like when I say polyacetate bonds, basically they are, if I have to write the example, cellulose acetate, right? Just we call them as rayons, rayon cloth, we also call it as rayon. Here you can also add buna N, buna S, all these are, we have already seen the structures, are man-made polymers. So let's come back and learn the next category, that is based on structure. Let's come back and see the next type of classification based on structure. So based on structure, they're classified into branched chain polymers, linear polymers, as well as cross-linked polymers. So when I have to write, branch chain polymers are also called as LDP, low density polyethene, or polymers, low density polyethenes or low density polyethenes. Here, high density polyethylenes. So when I have to speak about branch chain polymers, how should I write? Basically, branch chain polymers are straight chains. They have straight chains. In between, they also have certain branches also. So you can write these as branch chain polymers are straight chain polymers with branches in between. Here in linear polymers, there are no branches. All are straight chains, linearly arranged. These are straight chain polymers with no branches. With no branches. Now, these, when I come to cross-linked polymers, they are formed by bifunctional and trifunctional polymers. One linked to the other. Let us draw. I'll show you that. Cross-linked polymers are formed by bifunctional or trifunctional polymers. Done. So when I have to write the properties, so basically whenever you write LDPE, that means you have to write about low density property, low melting point. Opposite, when I have to write this, H stands for high density and high melting point. Here it is, in between. And how does this look? This basically has covalent bonds between them. Covalent bonds, has covalent bonds. So when I have to draw the branch in polymers, it is in this way, branch. Again this is branch. This is branch structure. Again this is branched in this way, right? So branched in this way. Again branched. When I have to draw the linear polymers, it is exactly linear, no branching observed. When I have to draw the cross-linked polymers, exactly, okay, this is, I should not make here because this is branched only till here. In the cross-linked polymers, you have one branch here, linked again, one more branch here, linked again, one more branch here, linked again. In this way, they have cross-linking which is formed in between the branches. One more in this way, all cross-linking. So this is your LDPE, HDPE as well as cross-linked polymers. Come back and do the third category of classification, that is based on molecular forces. Now whenever I speak about molecular forces, I have to tell the examiner whether they have weak forces of attraction or van der Waals forces or hydrogen bonding or dipole-dipole interaction. Those are the keywords. So based on the molecular forces, they are divided into four categories, that is elastomers, fibers, thermosetting polymers and thermoplastic polymers. Now first let us see the difference. So when I have to speak about elastomers property, how does that vary? Just we very well know, elastomers have the nature of having that elasticity, stretching character, isn't it? So elastomers are a class of compounds, a class of polymers which stretch on applying force. Right? To how much? 2 times of the length also they can stretch. Done. And when I speak about fibers, they are basically man-made. Done. They have their thin thread-like forms. Okay, let us write. These are man-made. These are also man-made, thin thread-like. Done. So when I have to speak about molecular forces, I have to concentrate more on forces. Now why are they stretching? What is the force present in them? This property is basically due to they possess weak intermolecular forces. Weak intermolecular forces of attraction. Forces of attraction. So because of this weak intermolecular forces of attraction, I can easily stretch them, and when I release, they come back to their original position. But here when they speak about forces, they are composed of hydrogen bonding, one concept which is making the bond stiff, strong enough, and they have dipole-dipole interactions. Then again it be dipole-dipole interactions. Again this makes the bond stronger. isn't it? Yeah, done. So here, because of the weak intermolecular forces, I can stretch it to twice its length. So right, you can add this point. They possess weak intermolecular forces of attraction, due to which, here I have not mentioned that point because I want to extend the answer to 3 marks, because if it is 3 marks, you can write 3 points and with an example and finish it off. So they possess weak intermolecular forces of attraction, due to which they can stretch twice the length. Okay, right. So when I have to write an example, I can write vulcanized rubber, vulcanizable rubber, vulcanized rubber can be the best example. We have already learned what is vulcanized rubber, so you can write that. So when I have to speak about this, because of this hydrogen bonding, I need to write the third point. You have tensile strength is very strong, so it has high, because the bonds are very strong enough, tightly held, isn't it? So high tensile strength, and what will happen to the elasticity? And low elasticity. Done. So because of this, they have high melting points. So if I have to write the example, nylon 66, I felt is the best example for writing fibers. Example, I could write many also, others also. Nylon 66, I felt would be a better example for fibers. Right, let's come back and see the next type of classification based on molecular forces only. It is a continuation of your elastomers and fibers. So basically, as names suggest, thermoplastic. This is thermosetting. So remember, setting means once it is set, once you heat it, it can't be reversible. So these are irreversible polymers. You can't revert back into its original position, original shape. So when I have to speak about thermoplastic polymers, simple. They have the properties in between elastomers and fibers. This is a class which, if they ask you for 1 mark, what is a polymer which has the properties in between elastomers and elastomers and fibers? That is thermoplastic polymers. Once again, they have properties between elastomers and fibers. So this is an intermediate one, thermoplastic polymers. So now important thing is thermoplastic polymers, when you are heating it, what will happen to both? So when you heat it, delta means heat, thermoplastic polymers, they become soft. When you cool it, they are going to revert back and they become, means they retain the shape and become hard. Means they are reversible. I can write reversible. If I have to come back to thermosetting polymers, when you heat it, they become an infusible mass. They come together and they become hard. You can't revert back while cooling. So on heating, they become infusible mass. That means they're going to combine and they set into a mass. They form a thick, hard mass, infusible mass. On cooling, does not revert back. It will not revert back its shape. That's why these are irreversibly cured, irreversible in nature. Irreversible in nature. Done. This is one. So let us write this as first point, write this as second point. Let us write this as first point, write this as second point. Now in the third point, I have to write an example. So thermoplastic polymers, if I have to say, as I said, it can regain its shape. So polythene, I can write. Like PVC, I can write. Done. If I have to write thermoplastic, resins. That is, what resins did we learn? We have learned bakelite, which forms straight chain and cross-linked polymers. So bakelite, formaldehyde resin. Because 1.5 mark or something, 3 points are more than enough for my resins. So this is your thermoplastic, this is for thermosetting. Once set, it will not revert back. Plastic, it will just retain its shape when it is hot, and when it's cool, it comes back to its shape. Right, let us come back and see the last type of classification, that is mode, or based on mode of polymerization. If it shows addition type, one after the other is added, that is a mode. Addition is a mode. And condensation, two bifunctional or trifunctional polymers, they condense, and every time water molecule or HCl or ammonia are removed. Let us write. So addition polymerization is basically, when I have to write, it is formed. How is it formed? By repetition of monomeric units. Repetition of monomeric units. So how do they repeat? Basically, they are going to form, they are going to follow step growth polymerization. Means one after the other, chain initiation, chain propagation, chain termination, in that way. So they are going to follow by repetition of monomeric units or addition of monomeric units. Okay, you can write it as addition of monomeric units. Done. By step growth polymerization method, which we'll be learning. Polymerization method. Here, when I have to write condensation polymerization, this you're going to write, it is formed by condensation of, we've already seen condensation polymerization, isn't it? Formed by condensation of two. It can be two, that is bifunctional. It can be three monomeric unit trifunctional polymers. Condensation of bifunctional or trifunctional monomeric units. Monomeric unit. This is done. Okay, yeah. So now, after the step growth polymerization, now during this process, what happens when they're condensing? There is elimination of, we have already seen, please watch that video, elimination of water molecule, elimination of ammonia, elimination of HCl in between. Watch the video, condensation polymerization, I have already done that. So if I have to write the example, because 3 points I need to write, I can write addition polymerization as PVC. We have written polyvinyl chloride, okay, polyethene, where every type polyethene one chain keeps on increasing. When I have to write condensation polymerization, we have learnt many, isn't it? Buna N is a condensation polymer, Buna S is a condensation polymer, nylon 6,6 is a condensation polymer, right? So nylons, so many things I've already discussed. So this is how you're going to write the differences in the exam. And see the types of polymerization reaction, the last topic of the chapter. So in types of polymerization reaction, we are going to learn about addition polymerization, that is a mechanism, as well as condensation polymerization. So let's write, what did I say just now? We have addition polymerization as well as condensation polymerization. So when I speak about addition polymerization, basically you have to remember three important concepts. Addition polymerization. So this is also called as chain growth polymerization. Means there is increase in chain, increase in length of the chain, polymeric chain. It goes on increasing, propagating. Chain growth polymerization. Done. Now, so for this, basically, what type of monomers? You're going to take a catalyst. You have a monomer also. So the catalyst which we are going to use are, it can be benzoyl peroxide, it can be acetyl peroxide, it can be tertiary butyl peroxide. It can be anything. Apart from this, we should also have monomers, because the catalyst is going to add to the monomer. So the monomers can be, the monomers should be either, it can be alkenes, it can be alkadienes and their derivatives. and their derivatives. Done? Done. Right. So this is going to increase. So basically this is going to follow 3 steps. What are the 3 steps? Let us write the steps, then come back to the mechanism. It is going to follow first chain initiation step, that is formation of free radical, chain propagation step, increase in the chain length, chain termination step where the whole reaction terminates and forms a complete polymer. So let us write, first it undergoes chain initiation step, second would be chain propagation step, third would be chain termination step. Okay, let us come back and see one after the other. Chain initiation, chain propagation, chain termination. Let's start with the mechanism now. So I said you require a catalyst or you also require a monomer. So basically when I have to speak about the first step, it is chain initiation. So in this chain initiation, what is the main concept? The main concept is formation of a free radical, which follows free radical mechanism. This you are going to write for the examiner to show that you are clear with the concept. Formation of phenyl free radical. This is what you are going to write. That means you're going in a right way to explain the examiner. So first you are going to take the catalyst, that is benzoyl peroxide. So what is the formula? So C6H5. Here also C6H5. Then you have C double bond O, C double bond O. I said peroxide. There is a peroxide linkage in the center. This is benzoyl peroxide. Now, first there is a shift. There is a breakage of the bond here. Exactly, it cleaves in the center. When it cleaves in the center, what do I get? This is till here one repeating unit, this is one more. So I can write it as 2C6H5, C, like see here. I can, this is breaking, isn't it? Right? So CO double bond O. Right? Fine. Okay, there is one more O also. So COO, I'll write like this. Yes. Further, there's a cleavage here and this is going to form C6H5 free radical above carbon. So this is called phenyl free radical. This is what I have written. Done. After this phenyl free radical is formed in the chain initiation step only, I said this is the catalyst. Now we require a monomer which should be an alkene, alkadiene or derivatives. So I am going to take that free radical. Done. I am going to join it with an alkene. This is a monomer. Right? This is your phenyl free radical. Now what happens when these two join together? Just see, the bond here breaks up and you get C6H5, C, single bond C, and this becomes a free radical now. This is propyl now. Done. Now we'll go back to the second step. Now chain has to propagate, isn't it? When I go back to the second step, that is chain propagation step. Chain propagation step. Now observe carefully. In the chain propagation step, this further adds to one more monomeric unit. This repetition goes on. C6H5, CH2, CH2 free radical adds to again one more alkene. So again this double bond breaks up and this joins. Now see here you have 3 plus 2, 5. This is going to form C6H5, CH2, CH2 is here. One more CH2, this bond breaks up and you have CH2 free radical. Now from 3 it has become 5. Done. So what is repeating in this? You're finding this unit is repeating every time. So you can put this as a repeating unit. So this goes on every time one more alkene adds in, it forms free radical. Now when it has to come to the chain termination step. Chain termination step. Done? Yes. Now observe carefully. In chain termination, like this, two free radicals are going to combine together. I am copying the same C6H5, that repeating unit, CH2, CH2 taken n times, and CH2 and CH2 free radical plus, I am going to write one more C6H5, CH2, one more CH2. Again, I am repeating the same unit, CH2 free radical. These two will join together. How are they going to join? When you just start, this should be one terminal, this should be one terminal. So write down C6H5 and one more terminal, C6H5. You have in between these, join them, CH2, CH2 terminal, then come here. So this becomes CH2 joined with one more CH2. Then you have this term, isn't it? Okay, I don't have place. I'm writing that here. So from here, I'm coming back to this point. You have CH2, again CH2. You have one more CH2. This is CH2, which is repeating, and the leftover C6H5. I'm writing it down. C6H5. Now let us see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is ending, terminating. This is also terminating with the repeating unit here. So this is your chain initiation, chain propagation, and chain termination. Right. After addition polymerization mechanism we have learnt, then the next type is condensation polymerization. So addition polymerization is always called as chain growth polymerization. Remember this. This is called chain growth polymerization because one step after the other is followed: initiation, propagation, termination. But when it comes to condensation polymerization, it is called step growth polymerization. One step, there is no link between one step and the second step. Everything is different. So I've already done under one video where I've named it as Terlin or Dacron. I've shown you the condensation and preparation of Terlin or Dacron, and where I also showed you like one Buna S, Buna N. Please go through the video. You'll have a clear explanation there. So addition, in the exam if they ask you, other name for addition polymerization is chain growth polymerization. Other step for condensation polymerization is step growth polymerization. So let us come back and finish off the chapter with differences between copolymer and homopolymer. Right, now basically we have done with the chapter. This is a summary, like basically they ask you what is the difference between homopolymer and copolymer. I listed out few for you all, so it's easy for you to remember. It's combination of all the topics together. So as we know, homo means similar. We have already done many examples for homo, just like your PVC we did, polyethylene we did, polystyrene we did. So if I have to write the differences, so as the name suggests, it is formed by addition of compounds, one after the other adds. Here they are going to form by condensation of compounds, true condensation, where you're removing water molecule, alcohol, ammonia, HCl, like that. So here, as the name suggests, again it has only single entity, single monomer, as homo means single. Co means two. There are two or more repeating units. And again, when I have to compare, it's a single unit, so it has a simple structure. This has a complex structure. I've been discussing the same earlier also. So you have examples of PVC, polythene, polystyrene. Here I've shown you the example of Buna N, Buna S, and Dacron also. So I've combined together in the form of a tabular column. Please study this and go. So with this, the chapter is complete. Everything is done in the chapter. Abnormal molecular masses, I think we have done in colligative properties also, the same topic. So let us come back and start with your board papers.